Gary Pratt here for Control Sphere Engineering. This video series will run you through a simple object-oriented industrial programming design, how to simulate that design, how to use simulation to improve the design, how to create your own reusable objects, and how to deploy hundreds of these objects with a few lines of code, and how to make objects configurable via a CSV file or OPC UA. For those of you who have not heard of object-oriented industrial programming, the term was coined to differentiate from the much more complex object-oriented programming used by computer scientists. For more information on object-oriented industrial programming, search for the term on the Control Engineering magazine to see a recent article, or visit my website, www.controlsphere.pro. I've been simulating my designs for over 40 years now, and while it takes a little longer to set up a simulation, I can say that 100% of the time it has saved more time than it consumes, usually much more time. I've applied this to control systems I've designed, as well as printed circuit board designs and FPGA designs. The ability to perfect the design in parallel to the plant or equipment being built, and the insight provided by the simulation, which would be difficult or impossible to measure on the target device, makes simulation invaluable. For this demo, we will create a simple tank level controller which will control the speed of the tank outlet pump to keep the liquid in the tank at a constant level, regardless of the flow rate entering the tank. The tank has an analog level sensor and a variable frequency drive motor controller for the output pump. To begin, we'll create a new program for our tank system and call it plant. We will create this in continuous function chart, as that is the best language to instantiate other objects. Then we will place 4 objects from our plant object library to control our plant. The first is an analog sensor. Remember, in object-oriented industrial programming, the goal is to create self-contained objects which carry out all the functionality necessary for that object, just like the engine in your car is totally self-contained. All you need to do is deal with its interfaces, the start button and accelerator pedal. This analog sensor object contains all the functionality necessary to interface with the level sensor on the tank. We will name this sensor tank level. We will push into this object to see exactly what is inside a typical plant object. As we can see, the analog sensor object has scaling for current to engineering units, high and low clamping, a noise filter, zero cutoff to avoid totalizing noise, provisions to allow the HMI to override the sensor, and then a series of alarms for excessive positive or negative rate of change, as well as high-high, high-low, and low-low alarms. The I/O for this object consists of inputs from the field as indicated with the _FI suffix, HMI inputs with the _VI suffix, configuration inputs with the _CI suffix, and program inputs with the _PI suffix. The physical I/O will be mapped to the _FI inputs as well as with a simulator, as we will see in a few minutes. We will show how the configuration inputs can be configured through a CSV file or an SQL database later in this video series. The HMI connections are typically made through the OPC UA. The outputs intended to go to the HMI have a _VO suffix, and the program outputs are indicated with a PO suffix. Returning to our plant design, we will instantiate a subtraction function to subtract the actual level from the setpoint level. We will add an input to the set the tank level setpoint and give it a default value of 80%. Now that we've made the connections, we can now remove the unused pins from our analog sensor to eliminate the unnecessary clutter. Next, we will add a PID controller from the OSCAT basic library. We will call it PID. Usually the control is more complex and we would create a separate function block for it, but in this case the control is simple. For the purposes of this demo, we will use a tank that takes 10 seconds to fill at full flow rate. Since the tank is a pure integrator, it represents a pole at 0 Hz and will have a gain of 1 over 2 pi f. For 1 Hz control loop, we will want a proportional gain to be the inverse of the tank. That would be 10 times 2 pi times 1 Hz. For now, we'll leave the integral and the derivative disabled. Finally, we will place a VFD object from the plant control library. This object provides all the logic necessary to control the variable frequency drive and communicate over its field bus. We will call it outlet pump. Our design is now complete. That is how easy it is to build a control system using object-oriented industrial programming. Next step is to build a simulator to simulate the plant. We will call this plant_sim and also build it in CFC. The simulator will mostly mirror the plant, beginning with the VFD simulator, which we will call outlet pump. Then we will place a tank simulator from the control simulation library. If you are interested in how simple it is to simulate a tank, we will push into this model. It consists of 3 lines of code. The first is to find the delta time since the last scan. The second is to perform the integration of the difference between the inlet and outlet flows. And the last is to limit the level of the tank. And lastly, we place an analog sensor simulator. Our simulator objects need a little more information about what they are simulating. To make this example respond quickly, we will make this a very small tank that takes 10 seconds to fill at full flow rate and a very fast acting motor that can slew at 500% per second. Lastly, we need to connect our simulator to our plant using the exact same full path names that we will use when we map the real I/O to the plant. The VFD simulator input will be mapped to the VFD output. plant.outletpump.speed_FO. The output of the analog sensor simulator maps to the input of the plant analog sensor, plant.tanklevel.input_FI. That's all it takes to create a simulator for this plant. Notice the simulation outputs _FI connect to the plant outputs _FO, and vice versa. This naming convention helps us know that we have made the right connections. The next step is to create a test bench. The test bench provides inputs to the system and records the outputs of the system. We could create HMI screens if this were an operator-driven system, but for this demo we will create a program to generate the test stimulus. Since this will be a test sequence, we will build the test bench from a sequential function chart. The first step will be to test the steady state. We will run this test for 20 seconds. On the steady state, we will create an entry action to set the system inputs. We will set the tank level set point to 80% and the inlet flow rate to 80%. Next, we'll add a dynamic step. And we'll make this run forever. For the dynamic, we'll add an active action and then have the tank level flow vary by a 0.2 Hz sinusoidal rate. We then need to assign our 3 programs to tasks. The plant goes to the default task, which is created for us when we open a new project. It has a default cycle time of 20 milliseconds. We assign the program to the task by dragging and dropping. The simulation task must run much faster since it is simulating the real world that runs in real time. I also like to make the simulation task run at a non-integer multiple of time to avoid any synchronization, which could mask potential problems. To do this, we create a new task called sim and assign it a 3 millisecond cycle time. And then we drag and drop the simulator and the test bench. The last step is to hook up our oscilloscope so we can see how the system is behaving. We will call this system and assign it to the same task as the plant is using. We will then view the tank level set point and the actual tank level in one y-axis. Then we'll create a second y-axis. And view the inlet and outlet flow rates. I can now log into the PLC that is running on my laptop, start the oscilloscope, and start the control system. The inlet flow rate goes to 80% and the tank begins to fill. When it reaches 80% set point, the outlet pump begins to run to keep the tank level steady. Although you will notice that there's a significant amount of steady state error in this control system with a tank level at over 81%. When the system enters a dynamic range, you will notice the speed of the outlet pump is varying to keep the tank level, but again there is significant error. But I'm sure some of you are saying that that error is too much. What can we do to improve the accuracy? I'm glad you asked that question. With simulation, it is very easy to test alternative control techniques. For example, let's try a second order control system. To do this, we will add some integral component to the PID which adds a pole 0 pair to the loop. The pole is at 0 Hz and we will place the 0 at our crossover frequency of 1 Hz by setting the gain to 1 over 2 pi times 1. Since the 0 has a gain of square root of 2 at its frequency, we will remove that from the proportional. However, now the loop will have nearly 360 degrees of phase shift at low frequencies, which will require some stability mitigation. We will add this by enabling the integrator only when the system is inside of its linear range. In other words, when the output of the PID is greater than 0 but less than 100. We will now log in again, start the trace, and start the simulation. Again, the tank begins to fill, but due to the instability, it now overshoots the set point and then rings a bit before settling out at a much better steady state accuracy and a much better dynamic accuracy. In addition to an oscilloscope, we can add a loop analyzer object to allow us to get a clearer picture of our control loop. To do this, we'll break the control loop at the output of the PID and add a Bode loop analyzer object. We connect the output of the PID to the stimulus in and the stimulus out back to the VFD. We also connect the output of the PID to the measure from and the stimulus out to the measure to give us a picture of the entire control loop. Since the control loop analyzer requires a system to be running in steady state, We add a new loop analysis branch to the test bench, which depends on a new analyze loop input. We'll give this an entry action which will set the steady state conditions and turn on the analyzer. We could look at the output of the analyzer in a CSV file it creates automatically, or from an Excel file via OPC UA, or we could just hook up another oscilloscope, and that's what we'll do. And we'll plot the frequency, the gain, and the phase. The Bode analyzer steps through the specified frequencies and measures the gain and phase around the loop at each frequency. This takes a few minutes, so instead we'll call up the results from a previous simulation. The top trace is the frequency, while the middle is the gain and the bottom is the phase. Notice the phase margin is nearly zero at the low frequencies. This is the reason for the instability. But the phase margin reaches 41 degrees at the 1 Hz crossover frequency, indicating that the loop will be stable and have an underdamped transient response. This concludes the first part of this demo, showing how simple it is to create and simulate a control system using object-oriented industrial programming. Additional videos will show how to convert this tank controller to a reusable object and create a farm of 100 tanks. An additional video will show how to configure all 100 tanks with a central configuration database. Gary Pratt here with ControlSphere Engineering. Hopefully you have seen part 1 of this 3-part video series and you are saying to yourself, those reusable plant objects are fantastic. How do I make one for myself? Well, I'm glad you asked. The next part of this video will answer that question. In the previous video, we created, tested, and perfected a tank-level controller system. Now let's say we have a pharmaceutical plant with 100 continuous reactors. Let's see how we can convert the tank controller we have into a reusable reactor object and deploy 100 instances of that object. We start out by cleaning up our workspace and then renaming our plant to reactor and changing it from a program to a function block. That's all it takes to change a program to a reusable object. We do the same for plant sim, but we also need to add a pointer to a reactor, so each instance of plant sim knows what plant it's connected to. In IEC 61131-3, a var in out is a pointer under the covers. Then we need to change the hard-coded I/O to associate them with a pointer which will be passed to the simulator when it is called. If you don't completely understand this, it will make more sense in a few minutes. We will call the pointer myReactor and swap that into the I/O path names. We do the same for the test bench, except now this needs pointers to both the reactor and the reactor simulator to which it will be associated. So we will add 2 pointers, myReactor and myReactor_sim. And while we are here, we will turn off the Bode analyzer. And just like we did in the simulator, we need to change the variables to the ones pointed to by the pointers instead of the hard coding which we did in the original example. The next step is to create a new plant sim, and test bench programs, which will instantiate and call 100 instances of their associated reactor, reactor sim, and reactor TB objects. To use the most effective use of time, we will implement the instances in an array. And since structured text is the best language to use for looping through an array, we will create this program in structured text. First, we declare an array of 100 reactors in the declaration area of the program. Then call all 100 reactors in a loop. That's how simple it is to deploy 100 instances of reusable objects. We follow a similar procedure for the plant simulator, except in addition, we need to pass each simulator a pointer to the reactor which it is simulating. Remember earlier we set up a pointer in the reactor_sim and used it to connect to the I/O. In this step we will provide the actual pointer which will be used to make that connection to the appropriate reactor. We do this by adding a reactor as an argument into the call to the simulator. Under the covers, the compiler passes a pointer to each of the 100 reactors to each of the 100 plant simulators. The simulator then uses the pointer to access the input and output variables of that reactor. We do the same for the test bench, except now we pass it a pointer to both its associated reactor and its associated reactor simulator. Lastly, we need to update our oscilloscope to connect to one particular instance. We can then log in, start the oscilloscope, observe the behavior just as we did before. The tank begins to filling up until its set point is reached, at which time the outlet pump turns on to keep the tank level at the near constant rate. The identical behavior is happening in the 99 other reactors. Up to this point, we've been using the soft PLC built into the CODESYS IDE. If we switch to the independent soft PLC that is running as an independent service under Windows, I can show you something interesting. To do this, we need to scan for and connect to the soft PLC in exactly the same way we would for a real PLC. The independent soft PLC is exactly the same runtime which is on any PLC that supports CODESYS. Using this, we can see that the performance will be if we deploy this project to a PLC with similar CPU hardware. To do this, we open up the Task Manager and look at its Monitor tab to see the statistics for the cycle time of the project. Notice that even though we are running second-order PIDs on 100 tanks, we are only using a couple hundred microseconds of CPU time. This really shows the power of compiled code under CODESYS with its custom compilers versus the interpreted code that many of its competitors use. Now you might be asking yourself how this would look if each reactor were in series, where the output of the one reactor feeds the input of the next. Interesting question. It's actually quite easy to do this. First, we're going to go back to the first order control loop to make the results more interesting. And then, so the system doesn't take 800 seconds for the liquid to reach the last reactor, that's 100 times 8 seconds to fill each reactor, we're going to modify the tank simulator so each tank starts out at 79% full. Then we will modify the plant simulator so that the first reactor simulator is called outside the loop, and the inlet flow of the simulator after that is connected to the outlet flow of the previous reactor simulator. Then we must unmodify the test bench so that it only interacts with the first tank. It's easiest to go back to the old test bench, so I will copy that from a different project. We aren't going to do a Bode analysis, so it's easier to delete the branch than to modify it, and the tank level set point is now set at each instance, so we will delete those lines. And finally, we need to vary the inlet flow only to the first reactor, so we will change that assignment in both actions. Now we change the oscilloscope so that it only looks at every 10th reactor, log in and run. We see the level of the tank, the next tank begins to rise after the level of the previous tank has reached its set point. The tanks are all working in series. That concludes this part of the demo. We have shown how easy it is to use object-oriented industrial programming to create a reusable object and to deploy hundreds of instances of that reusable object. And we have shown how those objects can be standalone or dependent on each other. Gary Pratt here with Control Sphere Engineering. In parts 1 and 2 of this 3-part series, we created and simulated an object-oriented design, converted that design into a reusable object, and deployed 100 instances of that object. Now hopefully you're saying to yourself, well, what if my reactors are different sizes and have different features? How do I differentiate each instance of a reusable object? Well, I'm glad you asked that question. In part 1 we showed the analog sensor object, which included a number of configurable inputs. In this part we will show how we add configuration inputs to the reusable object we built in part 2, and how this object connects to a central configuration service. It will also go through the features of this central service, which include the ability to create an editable CSV file containing the default values for all the configuration inputs of all the configurable objects, the ability to read this modified file at startup to properly configure all the configurable objects, and the ability to save individual configuration changes to allow tuning parameters to be captured and stored on the fly. The first step to making the reactor into a configurable object is to have the object extend the configurable base class. This gives the reactor all the functionality available in the config base class function block. The next step is to declare the configurable inputs. For this simple demo, we will make the PID inputs configurable. But typically, you will want to make your objects as flexible as possible with more configuration inputs. Notice we are using the _CI naming convention to designate the configurable inputs. The next step is to implement the interfaces, which are specified in the base class. CODESYS makes this easy with the right-click Implement Interfaces. We need to implement 4 interfaces: accept config, which receives the values from the central configuration service and writes the _CI variables; provide config, which provides a central tool with the current values of the _CI variables so it can write a configuration file with all the current values; provide config titles, which provides the central tool with the names of the _CI variables to use as a header row in the CSV file; set my type, which gives the function block name to the central service so it can group all the objects by type and insert a type header line. First, we delete the message that CODESYS adds to remind us to implement the interfaces. Unfortunately, CODESYS doesn't allow comments in the implementation of the interface specification, but it does allow comments above the method line. So we copy those comments from the declaration area into the implementation area, and we copy the assignment line example 3 times for our 3 PID configurable inputs. We repeat this process for the other 2 methods. Then we use Alt-Drag to grab the 3 configuration parameter names and paste them in each method. We also update the array numbers as well as the number that is passed back to the central configuration tool to check that the number of parameters match. We repeat this process for each method. Unfortunately, CODESYS does not provide a way for a function block to determine its own name, so we need to do that manually by placing the function block name in the setMyType method. This will be used by the central configuration service to group the configuration inputs by type and to place a type line above each group. Lastly, we delete the configured property. The base class takes care of that property for us. The next step is to create a task for the configurator central service and assign the configurator to it. And that's all it takes to make a configurable object. The next step is to go online, open the configuration service visualization, and have the configuration service create a template file. We do this by opening the configuration visualization and toggling the switch to write the configuration file. We can then examine and adjust the configuration parameters. The configurations for all the analog sensors are on the top. The first line shows us the names of the configuration parameters for the analog sensor. Each line after that contains the configuration values for each instance of the analog sensor. The next section contains a configuration for the 100 instances of the reactor object. The first column is reserved for the ISA name, and the next three columns are the three parameters that we created. Having the tool create this file for us saves us an enormous amount of time and potential mistakes over creating this file from scratch. We can now update this file with our own custom parameters. For this example, we will change the KP_CI parameter in the first reactor to 63 and in the second reactor to 64. This file is automatically read when a program starts. We can also read it using the visualization. Notice how the value of KP_CI has changed to the new value entered in the CSV file. The configuration service can also save the configuration of individual instances. This is a great way to manage tuning parameters. Say we have tuned the PID and found 64 to be the best value for reactor 1, but we only want to save the value of that one instance, not all the instances. We can toggle the store config_vi input on that instance, and it will have the configuration service write that individual value to a change file. We can then reread the config file, which will load the value we wrote into the CSV file, 63. We can then read the change file to read the individual value which we changed when we tuned the loop, 64. On startup, the config file is read first, followed by the change file. We can demonstrate this by performing a warm reset. Notice the value 64 is retained. This concludes part 3 of this video series. I hope I have shown how easy it is to create a configurable object and then to configure that object. The configuration service can be purchased from controlsphere.pro. Contact me for more information. I hope you found this video series interesting. If you'd like help getting started with object-oriented industrial programming, ControlSphere Engineering can help. Also with CODESYS training and consulting. Feel free to contact me at gary@controlsphere.pro.